All right, so on this lab,
It's just the square root. Yeah, it's square root of 4.
forever to write
Because
this lab.
you use,
So let me kind of explain what the big picture of the big idea is when I wrote this.
under a square root.
Is that this is a good lab, but it's not realistic in terms of like what you would actually see. But mainly because to try and actually do labs in real life involving the photoelectric effect is tough. Mainly because of the fact that the amount of electrons kicked off are usually really, really small. And if you remember back when we were trying to do the static electricity balloon, and you know, if you guys were near it, it completely screwed everything up because you
Don't
became
give
part
me
of the
that
system,
look, Danny.
and you all broke physics, okay? Well, I don't care. I think it was his hair's fault. So, this is why to actually do this, you have to have a very, very specific, highly technical apparatus. The values are extremely difficult to measure, and it just is horrible, okay? And you notoriously don't get good results. So the problem is if you try and actually do this, you get so wrapped up in the horrible experiment that you lose track of, hey, what's the big idea? So this is the cool part about this, is that you can fine-tune the wavelength of light. You can fine-tune the voltage. And you're not a part of the system, so you don't have to worry about you becoming charged and, oh, I'm negatively charged, and then that, you know, impacts the field, and it just becomes a train wreck to do. Now, the bad thing about this is that, number one, it portrays it like you can see the electrons, okay? You can't, when you actually do this, you obviously can't see the electrons. They're tiny, 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 tiny bits of matter, okay? But from a visual perspective, it works. So, you have three things that you can control in this lab. First is the wavelength. Now, you can either slide that wavelength and go, oh, 309, and it's going to show you what those are, okay? Or you can move it around. The other option is that if you go to the actual keyboard, I don't have a keyboard associated with this, but if you're doing this on your laptop, you can actually type in a specific wavelength. Okay, I can't because I don't have a keyboard with this, but if you're doing it on your Chromebook, you can actually say, hey, I want a wavelength of 550 nanometers or whatever you want that. So you can change that. You can change the intensity of the light. So you're at 32%, we can crank that up to 84%. Now, a quick refresher. When you change the intensity of the light, are you changing the energy of the photons?
No.
No. What are you changing? The number of photons, okay? You're not changing the energy of the photons, okay? So if I'm at 84% versus 32%, as long as it's the same wavelength, it's still the same energy. It's just how many do you have, okay? Now, down here at the bottom, this is where you can alter the voltage across the plates. So if you go to a positive, like I changed this to 3.8, and you'll be able to see this. So if you go to a positive voltage, this is going to make the right side of this positively charged, and it'll show you that. And the relative amount of voltage is kind of cool. It changes the number of positive charges that you see over there. Obviously, this is going to become negatively charged. So Lester said, if you move this where it's like barely 0.8, it reduces the number of positive charges. So it's like a visual way of indicating the strength of the electric field. So you can have positive voltage and you can have negative voltage. Okay, so if you switch over to negative voltage, this side is positively charged, that side is negatively charged. Basically, all you're doing is switching the direction and the strength of the electron field, of the electric field. Okay? So, you have three things. You can control intensity, wavelength, and the voltage. Okay, so those are your three things. So, as you go through this, the yellow sheet has the work functions that you need to use because those were developed specifically for this program. Okay, so don't use the work functions that were in the book. You have to use the work functions that are on that yellow sheet. So, here's the first thing that you want to do. Work function of sodium, this is in electron volts, caption, okay? So, determine the wavelength in nanometers such that the energy from the photon will just reach the threshold of the work function. So, in other words, Cohen is in jail. And the bail is set at 2.304 electron volts. You want to figure out the wavelength of light that if you set it to that value, it will just post bail. Then you want to click on there and actually enter that value in. Then, and if this is going to happen, you should see, like, and it's weird with this program. And I've seen this happen like in the same room. The math works, but sometimes it won't kick out an electron, and sometimes it will. Even though everybody in the room is running the same program, and everybody's typing in the same wavelength, it's just weird. So sometimes if you don't see an electron come out, don't flip out, okay? Look at the person beside you, they might have input the exact same thing, and they get this electron fairly moving across. So the math is good, just don't worry about that. Then, when you get to question number 5, so based upon your answer to number 4, is the wavelength correct in determining the work function? So basically, you want to change that wavelength by 1 nanometer one way or the other to see if it stops, to see if it continues to go. So that 1 nanometer wavelength is like a tipping point. So this is why it would be extremely difficult to do in an actual lab setting to fine-tune your light source to adjust it 1 nanometer either way on that light source. Okay? Virtually impossible to do. That's why this is such a cool program, because you can do that. In reality, it's tough to change it 1 nanometer because it's such a small value. So, sometimes, like when you get to number 7, you want to have it at 50% intensity. And then you want to have it at 100% intensity. So pay attention to what those intensities need to be. Then, when you get to number 8, you're going to change the target. So if you come over here to right up there underneath where it says FET, so you can change the type of metal that you have. So like in this situation, you can have copper. Come on. And it's cool because it even like changes the color so that it makes it look like copper on the plate. And then you're going to eventually have a mystery one, which we'll deal with later, okay? So the mystery one that's one of the things you're going to figure out is what that mystery is. So on this one, you have to pay attention to those specific like wavelengths. So when you get in the voltages, so on 10 and 11, you're going to change the voltage. In one situation, you're going to have a positive 0.2. One situation, you're going to have a negative 0.2. Pay attention to those values and then what's going to happen with the voltage. So when you get over to page 2, okay? So Conrad had asked, calculate the stopping potential based upon a work function of 2.304 and a 419 nanometer wavelength of light. So remember, stopping potential, usually measured in electron volts, is how much energy that it takes. So once that electron gets kicked off, how much energy does it take to stop it and make it go in the opposite direction? Okay, so it's like the catcher's mitt. What does it take to stop that electron? That's why it's measured in electron volts. You're eventually going to need to calculate the de Broglie wavelength of the electron and the velocity. So you kind of got to go old school kinetic energy kind of thing. Now, when you get to question 21, let me first tell you about question number 21 and how I do not want it answered. Do not answer. That was loud. Do not answer question number 21 in this space. There's not enough room. So question number 21 is a procedure. You're going to try and find the identity of the mystery metal. So here's the grand idea. You want to involve the light and you want to use the battery. So here's the broad idea. You're going to say, okay, hey, you're going to switch it to that mystery metal. You want to set a high enough energy of the photons that you get a current. So set your voltage to 0. So make this, let me kind of show you. There we got 0. And so I'm going to move this over here where it's like 370. And actually, okay. So this is this unknown metal. So I've got a low enough wavelength that I'm getting electrons being kicked off. Okay? And I've got a current of 0.021. So I picked a number. Boom, here we go. I got this. So then I'm going to adjust the current or the voltage on the battery so that I stop that. Now, if I make it a positive voltage, what do I make the electrons do? They just go faster, okay? Because they're just being pulled over there because I'm making the right side positive. So if I want to stop it, I want to have some negative voltage where those electrons just go across and they come back. So here's what you want to do. Set the wavelength so that you generate a current. Then find how much energy it takes to stop it. From there, find the work function. Knowing the work function, then you're going to go to the yellow sheet. And then, speaking of a lack of photons, and then from there you're going to find the identity of the metal based upon that work function. So your procedure should involve the steps, and it's going to be different for everybody. Everybody's going to pick a different wavelength. Everybody's going to have a different voltage. So you're going to tell me, hey, set the wavelength to this. Based upon that, here's the voltage that's going to stop it. Based upon that, here's the calculations that says, hey, this is how I'm going to find the identity of the metal. So if you can kind of get through 21 today, that would be cool. All right? We'll finish the rest of it up on Monday. So I'm done. So Danny's knocked down her camera.